Okay, today is another paper replication day, and so that means that we'll be going through a paper and some code. And so looking at this week, we have a recently published, well, in a journal, I should say. It's been on archive for a little while. One qubit as a universal approximant. Can't remember right now what journal it was published in. I think it might have been PRX, but actually let me just look that up. As one qubit as universal approximate. Let's see, APS. Oh, Physical Review A, my bad. It was just published like literally a few days ago, if I'm remembering correctly. And so, yeah, we're going to go through it and sort of, not a lot of the theory parts, but the experimentation, and we're going to recreate at least some of it. So, as usual, I'll link the paper. You can see it. Oh, I just realized I wasn't actually sharing that. But I'll write it here. One qubit as universal approximate. And so this is published by Pérez-Salinas. Sorry if I'm saying that incorrectly. And company, well, and et al. So that's what we're reviewing. I should note that unlike many papers, they do actually release their code, and I will link that as well. It's all available. They use Quibo or something like that as their quantum sort of circuit simulator. But I think what we'll see, or what I hope we can see from this, is that using TensorFlow Quantum is a lot probably easier. Maybe not, but looking at their code, it looks a lot more complicated than mine. But that's not to say TensorFlow Quantum is better. I'm just showing how easy things can be in TensorFlow Quantum. But I will link the paper and the code below. So now we can just sort of get right into it. The main concept is very similar to the data re-uploading paper. And so, right, you have some qubit here, and rather than just having the input here and then the gates, this goes out, the input goes into every layer. It's what's called data re-uploading, shown success in supervised and reinforcement learning in the QML world. So now we can get into it. The actual paper, there we go. This is the archive version, so no illegal shenanigans here. And so, yeah, so we can see, right, authors up here. Yeah, it was put on archive in February, so like 5 months ago. Abstract, introduction, who needs introductions, right? And so this is sort of the proof section. I guess they probably just do a different proof than the re-uploading paper, and they also introduce two types of universal approximates, the Fourier ones and the I don't know, they just call the other one the universal. So but there's some nice theory here if you like theory. I'm just gonna ignore it because who needs theory? But we can see here, this is the same idea that I've drew out before, right? You have the data coming in at each layer, and then the weights at each layer. You have the loss function and a classical optimizer. Some nice theorems. The key takeaway right here is, what is this unitary gate right here? What is this unitary operation in the in re-uploading, the data re-uploading paper? This was just a U3 of right, that was just the gate. But here they introduced, due to their proofs, they introduced some different techniques. So for the Fourier gate, it's this setup right here, which has in actuality 5 distinct single qubit gates, RZ, RY, RZ, RZ, RY, and here is the input data. And so you can see there's 5 different weights associated with each of these unitaries, and then for the other type, the UAT, there's 2 gates, and there's 3 of these. And notice here, all the other ones are single numbers, right? They're just a number for each layer, right? A single gate. If this is a single gate, right, and we have A, B, then A is just, 3.1 or something. But for these ones down here, for this W, right, this one allows X can be, well, I guess I should say, we have an arbitrary input allowed here, and then we have this weight is also arbitrary size. So it doesn't just have to be a single number that you're inputting. That being said, I do only input a single number as I don't implement this function right here. I treat both of them as single numbers in the code. So that is something to note. It's probably worth investigating, right? I was thinking about doing the same sort of Boston housing data set because that has 13 feature dimensions. But I just didn't do it. And the reason, I'll be honest, the reason I did is because I noticed this after I was like halfway through the code and I didn't want to go back and change it, but it really wouldn't be that much work. So now we get into the actual numerical experiments. They do a variety of one-dimensional functions using a sort of quasi mean squared error, but we'll just use normal mean squared error. So that's why I say it's not exact replication. They also do experimental. That's the real interesting part, right? It's probably the experimental section. But so these are the functions right here that they test on. We can see the classical, the simulation, the experimental. This is a 2-dimensional function that they have here. And this is just comparisons of performance with increasing layers. More graphs. And so the interesting thing is just that it works experimentally. That's pretty neat. And so, yeah, now let's just get into implementation, right? We have the basic idea here. So let's get into implementing it. I'll scroll up here, and I would encourage, I'll say this again, but if you're like looking for something to do, you want to get practice with iterable quantum, you want to better understand things, change this code to enable this right here. I'll say do this. This is what you could do. That would be a great experimentation. And I mean, honestly, right, you have some theory right here. I don't know, maybe you could read the theory, improve, make new proofs or whatever. But the experiments, right, this is producing this research is at the level that we're doing here, you can look at the code and if you just modify it, right, there's original research to be had very easily. And so I encourage people to play with it. Also, one thing to note is they use this lightweight, right? That's L is for the low memory version of BFGS. I don't remember whose names those are, but I just use gradient descent. And this is not like a big difference at all. The only, like, if you wanted to use this updater, you would change like one flag. It's not like this would require any code change, any substantial code change. At least it's just not as fast, and so I just wanted to use the fastest possible method. So now we can get into the code. So this is let me zoom in. So this is the custom layer, right, that we're modeling everything on. And so if you haven't watched the re-uploading video, I strongly encourage you to do that. before doing this because it builds a lot on that, and so understanding that will be important. So we have our depth and we have the type, right? Either the Fourier or the UAT. And so getting into it, right, we can say, okay, the number of each parameters is just the depth, because we're not dealing with this W weight matrix that can be arbitrarily large. Number of layers is just the depth, the type is this. So now if it's Fourier, right, we have the alpha, the beta, the lambda, the W, and the psi parameters. If it's the UAT, we just have alpha, psi, and W. We initialize these to be the 1 by number of parameter trainable variables. The number of parameters total in the system is 5, or 2 times the number of each parameters, because that's the number of gates, right? So when we're thinking about making the circuit, that's what this represents, right? Even though there's more parameters that we're learning, the number of parameters that the circuit sees is only 5 times this, because each gate is parametrized by a single value from the circuit end. We have our single qubit. We create our circuit symbols, and then we create our controlled quantum layer, which we create the circuit. We read out in the z direction on the qubit, and we use adjoint differentiation. We have our default blank input circuit, and then once again, and if you need more explanation, I recommend you check out the replicating variational quantum policies video for why this is here. But when we're mapping, I'll go back maybe to this. When we're mapping, when we're thinking from a programmatic standpoint, and we have these different, like this is alpha and this is beta, right? And this is, let's say this is the W, right? These are the weight matrices. We want to map, and we have our parameters, right? And so we want alpha, beta, W here, and then we want another layer. So we want this we're sort of slicing it this way. To keep track of these, I just append them. So we have alpha, comma, beta, comma, W, and then we reorder them. So we take the indices from each of them. And so that's what's going on there. And so that hopefully explains at least somewhat the idea there. And so, right, we want to say for each, if we're just concatenating them together, the index that we care about, the reordering that we do is that we say, okay, we take each, we take the place, right? So every index is offset by the number of each parameters, right? Because you have, let's say 10, right? 10 alphas, 10 betas, 10 Ws. So to get the first of each of them, you simply add 10 for however many that there are. And so that's what this J parameter controls. And then we iterate through and we get all the reordering of the indices. To make the circuit, right, if it's the Fourier, we have the RZ, RY, RZ, RZ, RY as specified. If we have the UAT, it's just the RY, RZ. And then we just make layer and layer of this. There's no entangling, it's just a single qubit. And then depending on the call, they're almost identical. And this is where getting a hang of this is important. So check out the variational quantum policies and the data re-uploading videos. So we get this batch size, we get we generate the input circuits, we tile the input numbers, right, to be the same. So if we have 100 input numbers, so it's let's suppose this is a 100 by 1, right, because we have 100 examples of 1. If we're doing multiplication row-wise, right, we want to multiply the weight of each unitary by the x value for however many unitaries there are. Then this has to be mapped to the number of u's, right? And so that's what's going on here. And so then that's what's going on here, I should say. Then we tile all the weights to match the number of the batch size. We do the operations on the actual weights that need to be done. Here we can see the inputs are getting modified. We concatenate them all together, and then we reorganize them so that the indices all line up, and we return the function called and the circuit with those parameters. Same thing happens down here. We reorganize the inputs, we tile the weights so that they match the batch size, and we get the input variations. We do the multiplications and stuff, and then we concatenate them, reorganize them, and return it. So that's the basic idea that we can see in this figure, right? We have, depending on the type, we have either that type or that type, and we have this going on here. So now we'll get into this loop right here, which is the optimizer and the loss calculation, which is really easy. We go over here, we can see we create the model, so we get the input of size 1. Oh, before we go any further, I do want to say, if you want to try and get this to work with the multi-dimensional inputs, you're going to want to change one thing, and that's in this. I believe they only write the, you're going to want to change right here. So it's only going to be compatible with the UAT type, but that's okay. You're going to want to change this to be, you're going to want to have an extra flag, and you'll want sort of the input dimensions here of the weights. And then actually that might honestly just be enough. The code down here might be robust enough that it just works independent of the size. I think you might have to modify the tile operations, but it's pretty much really probably easy to do. I just didn't do it, and so I really encourage someone to try it out. And if you do it, you can always make a pull request on the repo, and I'll incorporate the change. So yeah, looking at this now, we can see the inputs, we have the output, we have the layers, the depth basically, and the type for your UAT. We create the model, we use mean squared error, and we use the atom optimizer. And now these are the functions that we experiment with. We do the tanh function as the exact same in the paper. We do the polynomial function the exact same in the paper. We do, rather than using rectified linear unit, ReLU, as they do in the paper, I want to do something a little more exciting, so I just use the activation function MISH, which is described in that paper there. And that's what this is. It's just more complicated. And the Lambert W function. So for those of you who don't know, this doesn't really matter, but I'll just show it. The Lambert W function is the function that's the solution. So if we have, oh my God, I have too many things open. So if we have some equation, right? X e to the x equals y. Try and solve that for x. It's kind of hard, but you get that x equals the Lambert W function of y. And so that's what the Lambert W function is. It's basically the solution to this equation. And there's multiple branches of it. It's a whole thing. I'll link an explanation of it, but it's just a complicated function to that's the solution to this equation, basically. So yeah, getting into that, we have these functions, and then we can vary the number of layers. We have our typical early stopping callback, and then we iterate through the layers and the functions. We create the UAT model and the Fourier model. We create the training and validation data by uniformly sampling from -1 to 1. The testing data and plotting data is sort of out of distribution, just out of curiosity, really. Well, not out of distribution, but out of the exact training data range. It's the same function. And then we fit them using a batch size of 20 with early stopping for 200 epochs. We plot them, and then we save the plots. So I will go through and I'll show the results now. So you can see from the function name that this is the, I really shouldn't call it UAT. That's probably, let me change that, I guess, in the code. I'll just leave it for now. It's not UAT, it has both of them. But this is the plot of the function and the depth, right? So we can see the UAT doesn't do well, the Fourier, right? We can see the sinusoidal nature of the weights. We can see Pauli. You'll see this one is a big difference because I include outside of it and it goes to very large very quickly. And the actual paper, right? If I go, I'll show the actual results. Sort of what we're recreating right now is the figures right here, right? So this is, I just showed that one, and now we're doing this one. And you can see this is what it looks like, right? And that's because right here, there's a sharp up. And so we're including all of that. So yeah, that's why it looks weird, but you can still see it doesn't fit very well. Here's the mesh. That's what it looks like. Doesn't actually look that exciting, but once again, you can see with a single layer, it's not fitting very well. Here's a Lambert W. You can see it's a very strange looking function, but once again, doesn't fit very well. Now we can see better fits. This is 5 layers, 5 depth. And you can see you're starting to get there. You can see from -1 to 1, it fits very well. And then outside of it, you can see it's starting to go off, and that's because it wasn't trained on that. Here's the polynomial. You can see it fits very well, but it doesn't really get that curve, but that's fine. Here's the mesh function for 5 depth. It's pretty interesting. Now, Lambert W, you can see this one's probably the hardest, right? It hasn't fully gripped that sharp change. I mean, I don't know the exact testing points or training points, but I mean, these are the exact testing points. I don't know the exact training points, but that's interesting. Then this is 10 depth. You can see it fits very well, but starts to almost overfit, right? You can see it's going off even more so on either side. Here's a polynomial. Interestingly, it sort of curves up, the Fourier does. This one's interesting. Maybe something weird's going on here. That the Fourier is just really jank. I don't know what went on there. Same thing sort of happened with the Lambert W. That's just something weird. I don't know what went on with that, but maybe if you rerun it, it'll work out better. And so we can see, looking at this, let me look at the TNH. If we look at that and then we do that, you can see it's pretty similar. I'd say it's a pretty successful replication. So yeah, this is the code for replicating, quasi-replicating the recently published in Physical Review A, or I think is what it is, paper, 1 qubit as a universal approximant. As always, the code and everything will be